are different types. Those all are SR flip-flop, and second one D flip-flop, and third one JK flip-flop, and fourth one master slave JK flip-flop, and fifth one T flip-flops. So these are all the flip-flops we have, and we already discussed about the latches. Here the latches are the sequential circuits which are used to store the 1-bit data. And see, flip-flops and latches are similar, the sequential circuits, and both are used to store the 1-bit data. And but here we have some differences between flip-flops and latch circuits. Flip-flops and latch circuits. And coming to the latch circuit, these latches are asynchronous sequential circuits. Because of these latches does not work with the clock signal. Coming to the clock, here the clock is nothing but it is a time varying signal. And having particular frequency. Based on the clock signal also we have different types of flip-flops, and this clock signal is called as positive edge, and this is called as negative edge. So based on this clock signal also we have edge triggered flip-flops. And coming to the SR flip-flop, we will discuss about the SR flip-flops logical circuit and the truth table in this session. Okay, the logic circuit are the basic symbol for the SR flip-flop is, here we are giving two inputs, one is S and another one R, and S indicates this is a set and R indicates this is a reset, and we will get the two outputs, that is one is Q and another one Qn plus 1, or this is indicated with Q bar, and Q is the present state output, and the Q bar or Qn plus 1 will be indicated with next state. And here we have one input, that is clock signal. This is triggering input. Okay, and this is the basic block diagram of SR flip-flops. Coming to the logic circuits, here the cross-sectional connection of the two NAND gates or two NOR gates is called as latch. And here coming to the flip-flops, the cross-sectional connection of the two NAND gate and NOR gate, again here we are using another two NAND gates, and this is the two input NAND gate having two inputs. Here I am taking the NAND gate 1 and this is NAND gate 2, and another NAND gate, that is 3 and 4. And here we are giving the clock signal, and this is the first input S and this is second input R, and the output of the present state is reconnected to the fourth NAND gate, and the next state Qn plus 1 output is connected to the third NAND gate. So this is the logic circuit of SR flip-flop. Okay, coming to the truth table of SR flip-flop, here coming to the truth table of SR flip-flop, here when we are taking the two inputs, then we will get the 4 combinations, and here another input is called as clock signal. So that's why here we are taking 3 inputs. One is clock input, and S, R and Q, that is present state, and Qn plus 1 next state, and here we have one, that is state or comment. In last class we already discussed about latch circuit. When the clock signal is equal to 0, if the clock signal is equal to 0, and here I am giving S is equal to 1 and R is equal to 1, then 0 into anything is equal to 0, 0 ki complement, here we are getting 1 output. And similarly clock signal is equal to 0 for this NAND gate, and R is equal to, I am giving 1, then 0 cross 1 is equal to 0, 0 ki complement 1 here. So that's why here we are getting 1. Okay, and again here clock signal is equal to 0 and I am giving the S is equal to 0, then 0 cross 0 is equal to 0 and 0 complement 1 again, and R is equal to 0 I am giving, then 0 cross 0 is equal to 0 and 0 ki complement 1. So that's why whenever we are taking S is equal to 0 or 1 and R is equal to 0 or 1 in the presence of clock signal is equal to 0, then we will get the output of these NAND gates 1 and 2 is equal to 1. So that's why here I am taking S and R inputs are like X. That means either it is 0 or 1, and R input is also either 0 or 1. Okay, and again we have the clock signal Q present state input, that is anything, and then we will get the no change condition. That means if the Q is equal to 0, and 0 will be given for the fourth NAND gate, and 1 cross 0 is equal to 0, 0 complement 1 here. So here we are getting the output is equal to 1, and this one input is reconnected to the third NAND gate. Okay, 1 cross 1 is equal to 1, and 1 cross 1 is equal to 1, 1 ki complement, here we are getting 0. So if we are giving the Q input is equal to 0, then we will get the next state is equal to also we are getting 0, and if I am giving the Q is equal to 1 here, and 1 cross 1 is equal to 1, 1 ki complement 0. So here I am getting 0 output, and this output is reconnected to the third NAND gate, and 0 cross 1 is equal to 0, 0 complement 1. So output is equal to 1. So when we are given the Q is equal to 1, then we are getting the Q input next state is equal to also 1. So this state is called as no change condition. When we are giving S is equal to R is equal to any inputs in the presence of clock signal is equal to 0, then we will get the output is equal to no change condition. Whatever we are giving the input, the present state input, the next state input, output also we are getting no change condition. Okay, and clock signal is equal to 1 and S is equal to 0 and R is equal to 0, and we have the present state either it is 0 or 1. So here we have two inputs, that is Q is equal to 0 or 1. So clock signal is equal to 1 and S is equal to 0 and R is equal to 0, then we will get 0 cross 1 is equal to 0 and we will get the 1 k complement is equal to 1, and again 1 cross 0 is equal to 0, 0 complement here again 1. So in previous state, if the first NAND gate and second NAND gate is outputs are 1, that means active high outputs, then we are getting the no change condition. So we can write this is also no change condition. Okay, and next we have clock signal is equal to 1 and S is equal to 0 and R is equal to 1, and we have Q is equal to 0 and 1. So we have two inputs. If S is equal to 0 and R is equal to 1, S is equal to 0 and R is equal to 1, then we will get 0 cross 1 is equal to 0, 0 complement 1 here, and again 1 cross 1 is equal to 1, 1 k complement 0 here, we are getting 0 here. And if I am taking the Q is equal to, that means present state output is equal to 0, that 0 will be given for the fourth NAND gate as a active low input, and 0 cross 0 equal to 0, 0 complement 1 here. Okay, here we are getting the 1 output, and that output is connected to the third NAND gate, and 1 cross 1 is equal to 1, 1 k complement 0. So here we are getting the output is equal to 0. And next, if I am taking the Q is equal to 1, Q is equal to 1 and 1 cross 0 is equal to 0, 0 complement 1, and again 1 cross 1 is equal to 1, 1 k complement here 0. So here again I am getting the output is equal to 0. We already discussed that the 0 is indicated with reset and 1 indicated with set. So this state will be treated as reset condition. And the next state is the clock signal is equal to 1 and S is equal to 1 and R is equal to 0, and we will get the present state inputs is 0 and 1. 0 and 1, and take it as S is equal to 1 and R is equal to 0 here, and we will get 1 cross 1 is equal to 1, 1 complement is 0. So output of the first NAND gate is equal to 0, and the second NAND gate 1 cross 0 is equal to 0. Then here we are getting the output is equal to 1, and here the present state output I am taking Q is equal to 0, and for this state Q is equal to 0 and 0 cross 1 is equal to 0, complement is equal to 1, and 1 cross 0 here, 1 cross 0 is equal to 0, 0 complement here I am getting the output is equal to 1, and again Q is equal to 1. For Q is equal to 1 in this condition, and this 1 cross 1, that means this is the input for the fourth NAND gate, 1 cross 1 is equal to 1, 1 k complement 0, and again 0 cross 0 equal to 0, 0 complement 1. So whatever the present state inputs 0 or 1, then we are getting the output is equal to 1, then we will get this state is treated as set condition. And if the clock signal and S and R all inputs are active high, that means all the inputs are 1, and here I am taking the Q is equal to 0 and 1, then we will get the combination of S is equal to 1 and R is equal to 1, and I am taking Q is equal to 0. Q is equal to 0 and 0 for this state 1 cross 1 equal to 1, 1 Q complement 0, and again 1 cross 1 is equal to 1, 1 Q complement. Here we are getting the output of the second NAND gate is 0, and I am taking Q is equal to 0, 0 cross 0 is equal to 0, 0 complement 1, and 1 cross 0 is equal to 0, 0 complement here 1. So here we are getting 1 output, and Q is equal to 1. I am taking Q is equal to 1, 1 cross 0 is equal to 0, 0 complement 1 again, and again 1 cross 0 is equal to 0, 0 complement, here we are getting 1. Okay, so in this state here Q is equal to 1 and Qn plus 1 is equal to 0, and if Q is equal to 0, the Qn plus 1 is equal to 1. So this is the actual situation, and we have to get, when Q is equal to 0, we have to get the Qn plus 1 is equal to 1. So that's why this state will be treated as invalid or indeterminate state. So this is the actual working of SR flip-flop, and we have the truth table, and this is the logic circuits. And in the next class we will discuss about the D flip-flop, and we have different types of flip-flops like a JK flip-flop we will discuss in next class.